Hello and welcome to the part B of the module 3. Today will start neural network. In this part 1, we are going to discuss the basic understanding of neural network, the basic architecture of a neuron, which is the basic building block of a neural network. Then we discuss the single layer perceptron, basic architecture, and how the SLP is being trained. Then we discuss different application of single layer perceptron, and then we'll find what are the limitations of this single layer perceptron. The artificial neuron are very similar architecture with the biological neuron. So we would like to start the lecture with the structure of the biological neurons. A biological neurons has mainly three major parts. One is called cell body or soma. Then input to this cell body is called dendrite, and the branching output from the cell body, that is called axon. Now from other axon or other axon from the other neurons are coming to the dendrite of this neuron through an interface called synapse. So what happened? Some electrochemical signals which are coming to this cell body, some sort of functions that mainly is nonlinear functions are basically happened here, and based on this some thresholding or some logic, there is some sort of signal which are being outputted to the next neuron or neighbor's neuron through this axon and by these synaptic interfaces. So this is the basic idea of a very naive idea of this biological neurons. Now we'll try to understand what is the architecture or what is the structure of the artificial neuron. So this is the artificial neural network. This is the input layer, hidden layers and output layers, and one neuron is as a kind of, this is very similar to the biological neuron, and this is their structure is this. There is a, for example, there is n number of inputs like these dendritic inputs, something like that, and there is some sort of weighted, will come what is the functionalities of the weights. So these weights are multiplied with the corresponding inputs, and here in the body of the neuron, these are the summation of these weighted inputs. Bias is another special kind of input that is also weighted by this weight. So these weights are basically the parameters of these artificial neurons. Okay. Then this sum term is fed to a nonlinear activation function with the output. Now what are the role of these W1, W2 up to these weights and biases, and what is the activation function? These will all we understand in this course study. The one by one we'll see. Okay. Now first we'll try to start with an artificial neuron. That what is that we have discussed. Okay. So this in artificial neuron, what I have said, this is the basic building block of the ANN, and it mimics the structure of the biological neurons, also some functionalities of the biological neurons. Now here we can see there is a three main things. One is multiplication, that means x1 is multiplied with w1, okay, x2 is multiplied with w2, xn is multiplied with wn, and here this bias term x0 is multiplied with w0. So there is a multiplication is there. Then this multiplied or weighted inputs or weighted bias is getting added. So sum it up is weight take sum. So summation is also artificial neuron has this summation rule also. And then when we get this sum, that sum term is fed into a nonlinear activation function, that is activation. So there is the artificial neuron has three rules: multiplication, summation and activation, and then we get the output. So we can understand, but a very simple or very naive understanding of a artificial neural or artificial neurons. We have input, we have weights, this multiplied inputs are multiplied to the weights, we get the weighted input, sum it up and put it to the activation to get the output. Okay. Now, when we try to understand what is happening here and why, somewhat. So, these inputs are multiplied with corresponding weights that we have said. Now, this weight multiplication, if you see our biological neurons, there is some sort of prioritization of these electrochemical signals, and this thing kind of similar thing is here. So, these weight are weighted in W1. So, some sort of prioritization of the inputs is happening through these weights or weight parameters. And bias is also similar kind of thing. We'll see later bias, what is the role of actual bias. Now, at the body level, what happened? These weighted inputs are added. So, there is a series summation of these weighted inputs, and when we get the sum, we fed into the activation function to get the output. So, this is the very simple structure or simple functionalities of a artificial neuron. Now, before going to understand all this in very details, let us just take a look what are the different applications of neural network. So, neural network is very useful for nonlinear and complex problems, where these input-output relations are basically mathematically imposed. For example, image classification, speech recognition. So, mathematically imposed means one kind, we can say, if there is a 3 equations and 4 unknowns. This is one example of the mathematically imposed problems. Now, in addition, neural network is very useful pattern recognition. So, where we required to identify the patterns or regularities in the large data sets. For example, face recognition, handwritten digit recognition, and so on. Where the data rich problems, that means where the data volumes are very high, large amount of data, where neural network is very helpful, the recommendation system, sentiment analysis, etc. Where the data itself are very noisy or uncertain, situation where the data may be incomplete, noisy or inconsistent, then also neural network is very useful. Sense of data analysis, medical analysis, etc. And there is no explicit algorithm exist. Tasks where the clear step-by-step solution cannot be provided. Then machine translation, emotion detection like this. So these are the cases. Not only this, there is others also, but these are the important cases where neural network is very a powerful tool. Okay, so we'll start our discussion on neural network with a very fundamental and naive neural net. It's called single layer perceptron, or it's called SLP. The architecture, as we can see, that's very similar to a neuron. Okay, so what are the different components of the SLP? First of all, it adds some inputs, maybe let for our understanding the n inputs, and there is one bias term, and there is some weights, whatever we discussed as our neuronal structure. Okay, so each weights are associated with the particular input. Okay, now there is a bias term. That bias term we'll see later, that there should be some hypothesis function or decision boundary, and to shift some kind of, we can say DC shift kind of thing, that is basically used for this bias term, used for the shift of the decision boundary, that we will see in later part. So another thing is important here, that is called activation function. That we said earlier that a nonlinear activation function. Here we use a step function. So step function is basically a thresholding function. That what is the understanding, the mathematical description of the thresholding or kind of step function is something like that. If this summation, this kind of summation is basically greater than 0, it is 1, and if it is less than this summation is less than or equal to 0, that it is 0. So simple, this is the activation function. So what this SLP is basically doing is very similar to the neural one neuron what we have discussed earlier, that weights are up there and input are multiplied to weights, each inputs even the bias, and then this sum it up with all the inputs, and this sum is fed to this activation function. That means this summation term, if greater than 0, then output will be 1. If it is less than or equal to 0, then it is a 0. So that is the output. So this is the binary output, you can say, and it is used for binary classification. The output of the perceptor is binary, making it suitable for linearly separable. Now this is a very important thing that we will learn in the later of this lecture, that this SLP has a kind of limitation or weakness, that it can only model the problems which are linearly separable. So if there is a two-dimensional data point, there if they by a single line if can be separated, then only SLP can be used. Okay, these things we will discuss later in very detail. Okay. Now, before we going further, just discuss something about that binary step function. As we say, this binary step function is basically a thresholding function, something called threshold or Heaviside function, and that output a binary value based on whether the input crosses a fixed threshold. And if this is this x is this is the 0, that means if it is less than 0, it is 0, it is greater than 0, it is equal to 0, it is 1. So that is the 0 is the threshold, and fx is something like this. So generally this step function is in single layer perceptor for binary classification task. So at what we have discussed. Now with this background, we try to understand what actually this single layer perceptor is doing. Now what a neural net is basically doing, it's going to predict something. So there is some input, based on this input we can go into some output. Now before it can predict, that single layer perceptron is being trained. And if you recall that in our supervised paradigm, there is some examples or labeled examples are given, and based on these labeled examples we get these weights are such a way so that we can, given a input, we can get right output. That was the basic story. And how we can do it? Now please try to understand that there is a, when there is some input is given, then these inputs is given paired with a given output. So what is our purpose? We are find such W1, W2, Wn and W0, okay, so that this input to output mapping can be done without error or with a very less error. So this is a kind of mapping function that we are going to find out. That means this mapping function in case of classification is a decision boundary that we have seen earlier. Okay, so here there is a error when you predict something for a given set of data. This is that is the prediction, that this is I0 to IN WIXI, as what we have done here, that this prediction is there. Okay. And there is a some D, that is the actual or target output. Okay. Now this is two things, one is predicted output and is an actual output. So predicted output is like this. When it fed to the activation function, what is the output? This is the predicted and this is the actual output. And then we take a difference between actual output and predicted output, and this difference should be minimized. So as per our linear regression, holistic regression point of view, if we take this is an error kind of thing, that this is the error and this error is called cost or loss function, that should be minimized. The question is, how can we get this error minimized? So what we are basically seeing, that given these inputs, we have to find out such W1 to W1, these weights parameters, such that this whatever we are going to predict, that prediction is very close to the actual output. Okay, so the error becomes very less than close to 0. That is the basic understanding or basic agenda of training this single layer perceptron. The question is how? That we are going to discuss in the next few slides. Okay, now this is the training algorithm. So definitely what is happening at the very beginning, these W1, W2, Wn are basically initialized. That is called the parameter initialization. This initialization is very inaccurate. Maybe you can put everything 0 or everything some random values, even W0. Then we make this x1, x2, xn, and we know the corresponding output, since it's a labeled data, so we can do this. And definitely, since these weights are not randomly taken, then there is some error. This error is being used to change these W's or these parameters, weight parameters, such that this weight itself is being reduced, and that is going to say that weight updation algorithm. Okay, we use that. How we generally going to do it? Generally use the gradient descent kind of thing here, but in every iteration the weight are being updated in such a way that this predicted output, that means this difference predicted output and actual output, will be less than the previous iteration, so that we can going to get some inputs, or we can say some output given some input will be much closer to the intended output. And this is going first iteration, second iteration, up to kth iteration, and so where we can get the output is very close or the difference is basically less than a given threshold, so that we can say that our network is converged, or we can get this input to output mapping function, so that given an input function we get the intended output, so we can get the corresponding W1, W2 and Wn and W0. So this is the basic understanding of a training algorithm of single layer perceptron. Okay, now we are going to understand the training algorithm of single layer perceptron. So there is two output as we discussed previously. One is the predicted output, that is basically our model is going to predict this output, which is capital D, which what is this? This is I is equal to 0 to n. So, we are summing it up to all the n samples, and this is wi xi. So, all the wi xi's are basically summed up to all the samples. For easier to understand, in this case we assume that our activation function is linear x equal to fx. So, this d is now this, sum it up, I is equal to 0 to n wi xi, and this small d is the actual or target output. So, what is the error? Error is basically the squared error between capital D minus small d square, and it is normalized by 2. So, what we require to do? We have to find out such wi's so that this term, this error term or square error term is minimized. So, what we will generally do for any minimization problem? Take the gradient of this error. It is called error gradient with respect to these wi's. Wi are different weight parameters. So, if we do the differentiation of this, it generally comes half of it, just this will cancel it up, d capital D minus small d, del of capital D minus small d by del of wi's. Now, since this small d is constant, because it is a target, it is a constant. So, this del of capital D minus small d by del of wi, this is basically become del of capital D by del of wi's. So, now we have to calculate this del of capital D by del of wi. Okay. Now, this is what? This is, we put these values of capital D here. This is sum of equal to 0 to n wi xi. Now, we just notice one thing here. It is what? w1 x1 plus w2 x2 dot 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 wn xn plus w0 x0 as a biased. Now, what will happen for those which is not equal to wi? So, what it will become? It will become 0. So, only which is equal to wi that become. Then this di wi by dw is 1, so it is x1. So, this value is basically the xi for this wi. So, we can put this value here, del of E of by del of di. So, del of d of wi is basically d minus capital D minus small d xi. So, this is the your gradient, error gradient with respect to the wi. So, that is basically the idea of gradient. Okay. Now, what is required to do? We have to find out the wi so that it will be nice. So, what we have to do? We have to adjust this weight. So, from kth iteration to k plus 1 iteration, how wij is being changed? So, it's basically ij. So, ith neuron to jth neuron. So, this is what? wij of kth iteration minus this is eta, that is the learning rate, into this del E of wi. Okay, that will going to be the weight of the next iteration. Okay. So, if this is so, just put this value of here, this value will put it here. So, this is the weight updation algorithm. So, what we are basically doing? We are updating the weights in a subsequent iteration so that error will be minimized. So, in this kind of minimization problem, generally we use gradient descent. We have discussed this in the logistic case of logistic regression. Similar gradient descent can be used here. Okay, and in that case, get this kind of decision boundary will come, is equal to this sum it up of wi xi plus b. So what it look like? It is very much look like y is equal to mx plus c. So it is basically a line for a two-dimensional, if the data are given the bivariate or two-dimensional. So this is the training algorithm of the single layer perceptron. What we are essentially doing here, we are trying to find out this value or this equation, the values of wi, those wi which actually will give with this error function. This error function should be minimized. We are keep on adjusting weight so that we can find out the, if we plot the error surface, then it's basically a convex surface, so we can get the global minima there and we can find this. Okay, so this is the decision boundary of the SLP. So one of the important most thing, this SLP or single layer perceptron is a linear decision boundary. Basically gives a linear decision boundary. So this single layer perceptron can classify a data set which is linearly separable, and that is the most important thing to understand. Okay, so this is the way we are the training of SLP. Okay, now what is the different application of single layer perceptron? So different logic gates can be implemented in SLP which are linearly separable. So let us implement a basic Boolean function like AND or by learning weights that separate input patterns in hyperplane. So we are going to do some sort of example so that you can understand it. Some pattern recognition problem where we can use the linear separator. Just for example, the handwritten digit recognition. So spam detection with feature vectors. So this can be used. So binary decision system, that suppose medical diagnostic, disease presence absence, or a credit scoring kind of thing. So this, which is basically a straight line, is basically a separator or decision boundary. Or some control system that employs SLP for on-off control in engineering, like threshold based robot arm activation, simple sensor based trigger automation. So where the major thing is that where the decision boundary is a straight line or a linear hyperplane. Straight line for the two-dimensional case, linear hyperplane of the higher dimensional case. Now we can use this single layer perceptron. Now we are going to understand how single layer perceptron can be used to implement the simple logic gate. For example, AND gate. So as you know that this AND gate, the logic is this, for AND gate is 0 0 is 0, 0 1 is 0, 1 0 is 0 and 1 1 is 1. So these are the basic AND logic. Now if you plot this, then what we can say, if this is A axis, this is B axis, so 0 0 is 0, so this green plus is 0, 0 1 is 0, again this is 0 1, this is 1 0, and when only 1 1, this is this red plus. So there is a 3 points in one side and single point the other side. So this data representation, okay, can easily be separated out with a single or straight line. So we can say it is a linearly separable. So by a straight line we can, so it's a linear separator and we can easily separate it out, this 0 and 1. Okay. So this truth table of the AND gate, what is 0 0 0 0 1 0 1 0 0 and 1 1 1, this data representation is linearly separable. Now the question is how we are going to implement this. That we are being asked that you just implement a single layer perceptron for the AND logic. Now this our input is this x1 x2. So for in the case of A and B, we have put x1 x2, and bias term we assume all are ones. So what is basically do? We have to find out such W1, W2 and W0 so that these equations or this truth table can be met. So what we are going to do here, this thing that we put W1 is 1, W2 is also 1 and W0 is minus 1. This is just we put. Now why we put it? Just because of or just by inspection, that if we put this, then we can get this formation. Okay. So now you can see that here if it is x1 x2 0 0 and bias is 1, bias is always 1. So what will happen? That this x1 into w1, x1 is equal to w1, this 1 into 0, because this w1 is 1 is equal to 0, x2 into w2, then 1 into 0 again, and this bias term is minus 1 into 1, so minus 1. So ultimately what is the output? Minus 1. Now if we have used this activation, this kind of function, this yn if greater than is equal to 0, this is 1, it is less than is equal to 0 is 0. So output is 0 because it is less than 1. Okay. Now similarly if we go for a 0 1, similarly it is minus 1 because of this bias, this is 0 and this is 1, so ultimately it is 0, so it is equal to 0, so 0, so this is 0. Similarly this also 0 1 0, it is 0. But when it is the 1 1, then what is this? The summation term is the minus 1 plus 1 plus 1, so 2 minus 1 1, so it is greater than is equal to 0, so it's 1. So now we can what we get this particular thing, so 0 0 0 0 1 0 1 0 0 1 1 1. So this is the simple AND logic. So by inspection we can put W1, W2 and W0 such we find that this AND logic can be implemented by means of this single layer perceptron, and it can be done only because this logic, this data distribution is linearly separable. Okay. Now in case of training, one thing please be understood, this training, this formation, this W1 W0 we are not going to fix. This is just a application, that is how it is can be this single layer perceptron implement this. But this W1 W2 and W0 is automatically find out in that case of training, that you have to find. Okay. Then we go to the another example, that is OR gate. So the OR logic is what? OR logic is basically 0 0 0 0 1 1 1 0 1 and 1 1 1. So these are the basic. Here also these three red plus sign and is only one means, and it is also linearly separable. So here also we put it here that W0 equal to 0.5, and what we are going to find out that in this case yn, when both are 0, both input are 0, it is 0 minus 0.5, so it's less than is equal, and we can get this basically output 0. And when it is other combination 0 1, so 0 1 is basically this is 0, this is 1, and this is 0.5 minus 0.5. So it is basically plus 0.5 greater than 0. So it is 1. So if 1 0 it is 0.5 and 1 is 1 point for 1.5 means all this 1. So we can get this truth table or this logic table by this implementing this. So but in this way we can implement the OR gate. Okay, but here also please notice that this can be done by single layer perceptron because these data distribution to these groups are linearly separable. Now again take another example, that is if we want to do this XOR logic. Now we see the XOR logic is that 0 0 0 0 1 1 1 0 1 and 1 1 0. Now you can see please that if we plot this XOR logic, this XOR representation, so this kind of will come. Now here you could see, can you find a single line to separate this? So then we can see that no, there is no single line possible. At least 2 lines is required to separate it out. So this XOR logic, where these data points are not linearly separable, that cannot be done by single layer perceptron. So the perceptron can only solve the problems that are linearly separable. Problem more complex cycles are not linearly separable. So here it is a linearly separable problem. So there is a boundary, John boundary between these two. This is linear. But here, is there any linear separable line? So it's a non-linearly separable. Okay. So in this class, in this lecture, we discuss the neural net, we define the neural net, and we introduce the single layer perceptron. We have seen what is the training algorithm, what is the applications and the limitation. The next lecture we will discuss multi-layer perceptron. Thank you.